Hello, welcome to Guidancee Education channel. We are continuing Chapter 1 Electric Charge and Fields under Class 12 Physics. Let us see the topics covered in this video. Electric field lines for different charge configuration, properties of electric field lines, electric field due to multiple charges and significance of electric field. All these topics are under focus area for the examination. So watch the video completely without skipping, and if you think it is useful, do like the video, share the video with your friends who may also be benefited, and also leave your comments in the comment box below. If you have not subscribed my channel, do subscribe it now and also press the bell button so that you get intimated as soon as videos are posted. It will be a great motivation for me. Now, though I have given the time schedule for these various subtopics in the description box below, it is better that you follow the video completely. You will definitely be benefited by that. Okay, thank you. Now we will see electric field lines for a few charge configuration, that is charges placed in different methods. I have provided here 4 pictures. Let us consider the first one as positive charge. Single isolated positive charge. The field direction is outward. For an isolated single negative charge, the direction of the field is inward. The third picture shows the field line for 2 leg charges. Let us assume these 2 charges are positive charges. Then their field lines will diverge outward. Since they are like charges, you can notice that these field lines are repelling each other. One important aspect of electric field lines is that in 3-dimensional space, they are really curved. But we represent these lines as straight lines. It is justified as the tangent drawn to these curved lines at any point will be a straight line. Say for example, this is a field line. We choose a point here and draw a tangent. Then this is the direction of the field line. So it is straight. So it is represented as straight lines. But you should remember that field lines are always curved in space. Okay. If the 2 charges considered are negative, the representation of their fields will also be the same. The only difference will be the direction of the arrow will be inward. Anyway, I have not made a separate diagram for that. You can very well understand that it is a very simple concept. Now the last diagram. 2 unlike charges are close by. That is, one charge is positive and the other is negative. 2 unlike charges separated by a small distance is called dipole. We know unlike charges attract. Electric field lines start from positive charge and end in negative charge. I have shown this only for 2 field lines, not for all. Please note that the distance between 2 adjacent field lines is greater at this region than nearer the charge. For the examination, you may be given some of these pictures, and you may be asked to identify the type of charge configuration. Some one-word questions also may be asked from this portion. Okay. We are familiar now with the field line representation for different charge configurations. Now we will see properties of electric field lines. First property, field lines start from positive charge and end in negative charge. Second one, in a charge-free area, the field lines are continuous. Do you know what charge-free area is? It is an area where there is no charge already present. If another charge is already present there, then the shape and nature of the field line will change. Third one, 2 field lines never cross each other. Fourth point, the field lines never form closed loops. I will explain that. If this is the positive charge and this one negative charge, then the lines originate from positive and end in negative. That is, these lines will never come back to the origin. That is, they don't form closed loops. These are the properties of electric field lines. Now we will see electric field due to multiple charges. That is, what will be the electric field in a location when a large number of charges are present in that location. We have already discussed electric field due to isolated single charges in the previous video. If you have not watched it yet, click the I button in order to watch it. Under Coulomb's law, which speaks about force due to charges, we discussed force due to multiple charges on another charge. Please don't confuse this video with that video. Understand it clearly. You can click the I button in order to watch that previous video. Now let us come back to this video. Electric field is a vector quantity. If a large number of charges are present in a location, the total electric field due to all these charges will be the vector sum of the electric field due to each individual charge. Electric field due to multiple charge can be determined using Coulomb's law and the principle of superposition. Principle of superposition is essentially the addition of vector quantities or vector addition. Consider a system of a few charges. This is one charge, another charge, yet another charge, and say one more charge at a certain location. Consider a location P at a certain distance from these charges. We want to determine the electric field at P due to the charges Q1, Q2, Q3 and Qn. Let the last charge be N. We are considering several charges. Electric field at P is the vector sum of electric field due to all these charges. Let the distance of Q1 from location P be equal to R1, distance of Q2 R2, distance of Q3 equal to R3 and distance of Qn equal to Rn. These are the corresponding position vectors. Let us take the distance of P from all these charges be equal to R. Then ER is equal to sum of electric field at P due to Q1, which is ER1, electric field at P due to Q2, which is ER2, and electric field due to Q3 at P, which is ER3, and finally electric field at P due to Qn, which is ERn. We have applied the principle of superposition. All these individual electric fields due to these individual charges can be represented using Coulomb's law. Then ER1 can be represented as 1 by 4 pi epsilon naught Q1 by R1, that is distance of P from Q1, raised to 2 into R1 P cap plus 1 by 4 pi epsilon naught Q2 by R2 P raised to 2 into R2 P cap, and so on till the last charge, plus 1 by 4 pi epsilon naught Qn by Rn P raised to 2 into Rn P cap. If you have any doubt regarding the vector form of Coulomb's law, please click the I button in order to watch that. 1 by 4 pi epsilon naught is common. Therefore, we will take that quantity outside the equation. Then we will write it as 1 by 4 pi epsilon naught sigma Qi by Rip raised to 2 into Rip cap, where I has the limit from 1 to n. Now, this is the expression for the total field at a location due to a system of n number of charges. This is a very simple thing. It can be easily understood. The only thing is you should have some patience and follow these steps in a very systematic way. Now that we have finished discussing the details of electric field, we will see the significance of electric field, because we already have a quantity electrostatic force. Then what is the need for electric field? Significance of electric field. Electric field is represented by the letter E. So throughout we will be using the symbol E wherever we want to use electric field. Okay, let us see the first point. Electric field is not a mathematical concept. It really exists. We have already proved in the previous section that when a test charge is placed near a source charge, the test charge experiences the field of the source charge. It is the interaction between the electric fields of the source charge and the test charge which causes the force. Next one, the electric field characterizes the environment around a system of charge or a single charge. Let us note that electric field is a vector quantity. What is the meaning of system of charge? It means more than one charge. What do you mean by environment around the charge? That is how the electric field is felt there. The nature of the electric field depends upon the nature of the electric charge configuration. We have just seen that the electrical environment around a positive charge or a negative charge or two like charges or a dipole is quite different. That is what the electric field lines tell us. So that is what is mentioned here. Third point, the electric field tells us the force that is experienced by unit charge kept in that location. That is whether it will be attracted or repelled. Fourth one, electric field varies with location in space. We have seen that the variation in electric field is proportional to 1 by r square, where r is the distance of the location from the charge. Electric field is independent of the test charge Q. What does this mean? It means that whether a test charge is placed or not, there is a field all around the source charge in three-dimensional space. Test charge is used only to demonstrate electric field. The concept of electric field becomes more relevant and significant in explaining the time lag in the accelerated motion of a charge due to the motion of another charge in electromagnetic phenomena. Let me first explain what is electromagnetic phenomena. Static charges have only electric field, but moving charges have electric field as well as magnetic field. Hence, electromagnetic field, and the phenomena is called electromagnetic phenomena. This is a charge, and imagine that it is moving in the direction shown by the arrow. What does this concept tell us? It tells us about the time lag in the accelerated motion of a charge due to the motion of another charge. Consider another charge in its vicinity. Suppose this source charge Q starts moving in this direction. Then this test charge also moves and its motion is accelerated, that is, velocity increases. But it starts motion only after some time. That is, there is a time lag in the motion of the test charge. The explanation for this lag is best given by the concept of electric field. The source charge develops electromagnetic field, and then only the test charge Q will experience that field. So there is a time lag. I hope these points are clear. We will meet in the next video with another important topic. Thank you.